For decades, humanity has been on this epic scientific quest, really. The goal? To harness the power of the stars themselves, to literally build a sun right here on Earth. So in this explainer, we're going to dive into the absolutely incredible world of nuclear fusion. So why this massive effort? What's the point? Well, the stakes could not be higher. The promise of fusion, and this quote really nails it, is nothing short of a complete transformation of our energy future. We're talking about a source of power that's clean, incredibly abundant, and could last for millennia. One that doesn't create greenhouse gases or the kind of long-lasting radioactive waste we get from our current nuclear plants. All right, here's how we're going to break it all down. First, we'll talk about the incredible promise of fusion energy. Then, the monumental challenge of actually creating a star here on Earth. We'll look at the two main ways scientists are tackling that problem, get a sneak peek inside the wild machines they're building, and finally, ask that big question, is fusion really our future? So let's start with that core motivation. Why are literally thousands of brilliant scientists and engineers all over the globe dedicating their entire lives to this one single goal? It all boils down to this one beautiful process: nuclear fusion. It's what powers our sun and every star in the sky. Basically, you take two really light atoms, usually special heavy types of hydrogen, and under just insane heat and pressure, you force them to combine into one heavier atom, helium. Now, here's the magic trick. The new atom actually weighs just a tiny bit less than the two original atoms did. And that little bit of missing mass? It gets converted into a huge amount of energy. That's Einstein's famous E=mc² in action right there. Okay, so that sounds simple enough in theory, right? But actually trying to do it here on Earth, well, that is the ultimate engineering challenge. We have to somehow recreate the conditions inside the core of a star. No big deal, right? Here's the problem in a nutshell. First, you've got to take a gas and heat it up until it becomes a plasma, this superheated fourth state of matter. We're talking millions of degrees, actually hotter than the sun's core. And then, somehow, you have to hold that incredibly hot, unstable plasma together long enough for fusion to actually happen. So the big question is, how on earth do you build a container for something that hot? To solve that mind-bending problem of confinement, of how you hold a star, scientists are basically chasing two main strategies. Two very, very different paths that lead to the same incredible destination. On the left, we've got what's called magnetic confinement. The best way to think of it is like a magnetic bottle. Since plasma is full of charged particles, you can use these ridiculously powerful magnetic fields to trap it, to hold it in place so it never touches the walls of the machine. Then on the right, you have a completely different approach, inertial confinement. This is less of a bottle and more of a cosmic squeeze, where you use brute force to crush a tiny target. Let's dig into that a little deeper. The magnetic approach, which often uses a donut-shaped machine, is all about holding the plasma steady for a long time. It's kind of like a marathon. The inertial approach, on the other hand, is a sprint. It's a sudden, unimaginably powerful burst. You use the world's most powerful lasers to just blast a tiny little fuel pellet from every direction at once, crushing and heating it so fast that fusion happens in an instant, before the whole thing can blow itself apart. So now let's move from the theory to the hardware itself. And I have to tell you, these aren't just ideas on a blackboard. These are some of the most complex, most awe-inspiring machines ever conceived by human beings. And the scale of this whole effort is it's truly global. Take the flagship project for magnetic confinement, a machine called ITER, which is being built right now in the south of France. This isn't one country's project. It's a massive international collaboration with all these major global powers pooling their money and their best minds to build one single device. That's how important this is. This should give you a sense of the insane complexity we're talking about. What you're looking at here isn't the whole machine, not even close. This is just one component. It's part of the antenna system they use to heat the plasma up. Every single piece of these machines is a custom-built, high-tech marvel. And then, for the other approach, inertial confinement, you've got facilities that look like this. This is the laser bay at the National Ignition Facility, or NIF, in the US. What you're seeing is an area the size of several football fields, packed with equipment designed to create the most powerful laser beams on the entire planet. So, what exactly do you point all of that energy at? You point it at this, I'm not kidding. That entire massive facility, all of those unbelievably powerful lasers are focused with perfect precision onto this one tiny target. It's this beautiful, meticulously engineered capsule, usually smaller than a peppercorn, that holds the fuel. The contrast between the immense scale of the machine and the microscopic target is just, it's mind-blowing. So all of this incredible science, all of this investment, it all leads to the one big question that I know you're thinking. When is this actually going to be powering our homes? When will fusion energy be a real thing? While the projections most experts are looking at right now point to the first commercially viable fusion reactors coming online sometime between 2040 and 2050. Now, I know that can sound like it's a long way off, but when you think about what we're actually doing here, developing a fundamentally new primary energy source for all of humanity, in that context, it's practically just around the corner. So here's the key takeaway. The quest is very much on, and we're at a really critical moment. Scientists are hopeful they'll achieve ignition, that's the magic point where you get more energy out than you put in, within this next decade. But we got to be realistic. There's still some huge scientific and engineering hurdles to get from one successful experiment to a reliable power plant that runs 24/7. This journey has been a long one, filled with so many setbacks and so many amazing breakthroughs. But when you see these incredible machines pushing the absolute boundaries of what we thought was possible, it leaves you with this one final, thrilling thought. After all this time, are we finally on the verge of capturing the fire of the sun?